Hello, welcome. In this short video, let us look at the definition and an example on the CRB, that is Kramer-Rao bound, on a vector of parameters. That is, given the probabilistic model P of x with the parameter theta bar, that is a parameter vector theta bar, where theta bar consists of p parameters, that is theta 1, theta 2 up to theta p. That means the parameter vector has p components. So this is the vector of parameters. And then provided that the estimator theta I hat is an unbiased estimator, then the variance of the estimator theta I hat is bounded by the ith diagonal element of the inverse of the Fisher information matrix. That is, I of theta ij, that is the element in the ith row and jth column of the Fisher information matrix, is given by minus expectation of the derivative with respect to theta I and theta j of the log likelihood function. So this definition or this expectation gives the element in the ith row and jth column of the Fisher information matrix, and once you determine the inverse of this matrix, the diagonal elements of this inverse matrix give the CRBs for the parameters theta 1 to theta p. So that is the CRB on a vector of parameters. Now let us look at an example. Consider a linear model x of n, which is equal to a constant a plus a noise component w of n, where w of n follows a normal distribution with mean equal to 0 and variance equal to sigma square. As a result, the observation model x of n follows a normal distribution with mean equal to a and variance equal to sigma square. Now our parameter vector theta bar is given by the mean and variance of this distribution, that is a and sigma squared. So basically we assume that the parameters a and sigma square are unknown and we want to estimate them. Now in order to calculate the CRB for these two parameters, we have to first set up the log likelihood function, that is L of the parameters a and sigma square, which is given by logarithm of the probability distribution of the vector of observations x and the parameter vector theta bar. This can be simplified as logarithm of the product n equal to 0 to n minus 1 probability distribution of x of n, where x of n is the nth observation with the parameter vector theta bar. And we already know the probability distribution x of n with the parameter vector theta bar as a normal distribution. So by using the definition, we have logarithm of the product n equal to 0 to n minus 1 by square root of 2 pi sigma square exponential of minus x of n minus a whole square divided by 2 times sigma squared. So this is the log likelihood function with the parameters a and sigma square. Upon simplification, this becomes summation n equal to 0 to n minus 1, because logarithm of a product becomes summation of the logarithm. So this becomes summation n equal to 0 to n minus 1 log of 1 by square root of 2 pi sigma square exponential of minus x of n minus a whole square divided by 2 times sigma square. Upon simplification, this becomes minus n by 2 logarithm of 2 pi sigma square minus summation n equal to 0 to n minus 1 x of n minus a whole square divided by 2 times sigma square. So that is the final log likelihood function. Now we want to calculate the elements of the Fisher information matrix, that is I of theta bar for each row and column equals minus expectation of the double derivative, where one derivative is with respect to theta I and the other derivative is with respect to theta j, that is dou square by dou theta I dou theta j of the log likelihood function. So by using this definition, we can calculate the elements of the Fisher information matrix. So first we determine the derivative with respect to the parameter a, which is equal to the derivative of this log likelihood function with respect to parameter a, which is clearly minus 1 by 2 sigma square summation n equal to 0 to n minus 1 2 times x of n minus a into minus 1. And obviously the derivative of the first term is equal to 0. So we are left with 1 by sigma square summation n equal to 0 to n minus 1 x of n minus a. So this is the first derivative with respect to a of the log likelihood function. Next we look at the derivative with respect to the parameter sigma square. It is dou by dou sigma square of the log likelihood function is equal to the derivative of the sum of this term with respect to sigma square. Obviously for the first term it should be equal to minus n by 2 times sigma square. And for the second term, the derivative is with respect to 1 by sigma square, and the rest of the sum can be treated as a invariant with respect to sigma square. So we have minus 1 by 2 into minus 1 by sigma power 4, that is derivative of 1 by sigma square, into the summation n equal to 0 to n minus 1 x of n minus a whole square. Now let us look at the second derivative with respect to the parameter a, that is dou square by dou a square of the log likelihood function, which is the derivative with respect to a of the first derivative right here. So it is 1 by sigma square into derivative of x of n is 0 and derivative of a or minus a is minus 1, and we have n terms here, so we have minus n. So this is equal to minus n by sigma squared. The derivative, the double derivative with respect to a and sigma square is equal to the derivative of this term with respect to the parameter a, which is 1 by sigma power 4, that is the term here. So 1 by 2 times sigma power 4 into derivative of this sum, which is summation n equal to 0 to n minus 1 2 times x of n minus a into minus 1. So clearly this is equal to minus 1 by sigma power 4 summation n equal to 0 to n minus 1 x of n minus a. So this is the double derivative, where one derivative is with respect to a and other one with respect to sigma square. And finally the derivative, the second derivative with respect to sigma square, that is dou square by dou sigma square square, we have logarithm of the log likelihood function is equal to the derivative of the next derivative of the term here with respect to sigma square, which is clearly equal to minus n by 2 into minus 1 by sigma power 4, that is the derivative of this term, and then the derivative of 1 by sigma power 4, which is clearly minus 2 by sigma power 6. So we have minus 2 by sigma power 6 summation n equal to 0 to n minus 1 x of n minus a whole square. So this is the second derivative with respect to sigma square. Now we can determine the expectations of these derivatives. So the first term in the Fisher information matrix should be the expectation of this second derivative with respect to a. that is negative expectation of this second derivative, which is negative expectation of the second derivative with respect to the parameter a of the log likelihood function is clearly equal to n by sigma squared. And from this term, the negative expectation of the double derivative with the parameters a and sigma square of the log likelihood function is equal to, since the term is minus 1 by sigma power 4 into the summation of the difference x of n and a, we have 1 by sigma power 4 summation n equal to 0 to n minus 1 expectation of x of n minus a. And clearly this expectation is equal to 0 since expectation of x of n is equal to a. So this is 0. That is, the off diagonal elements in the Fisher information matrix are 0. And finally, the expectation of the second derivative with respect to sigma square is the expectation of this term, which is clearly equal to the negative expectation, of course, of the second derivative with respect to sigma square of the log likelihood function is equal to expectation of n by 2 into sigma power 4, which is clearly equal to minus n by 2 times sigma power 4, since there is a minus here. 1 over 2 here from the, so we have 1 by sigma power 6 summation n equal to 0 to n minus 1 expectation of the difference x of n minus a squared. So the definition of the variance of x of n is basically expectation of x of n minus a squared. So by using this definition, we can replace this expectation with the variance sigma square. So we are left with minus n by 2 times sigma power 4 plus 1 by sigma power 6 into n times sigma squared. Clearly, this is equal to n by 2 times sigma power 4. So by looking at the results from the different expectations, we can write down the Fisher information matrix as I of theta bar is equal to I of the parameters a and sigma squared is equal to the matrix n by sigma square for the first term and 0 for the off diagonal elements, and the next value or the last value, that is the value in the second row and second column, is that is the n by 2 times sigma power 4. So this is the Fisher information matrix. Now we can easily invert this matrix since this is a diagonal matrix. So we have I inverse of the parameters a and sigma square, that is the Fisher information matrix. The inverse of the Fisher information matrix as sigma square over n and 0 and 0 and 2 times sigma power 4 by n. Therefore, the CRBs on the estimators a hat and sigma square hat are variance of a hat is bounded by sigma square over n, and variance of the estimator sigma square hat is bounded by 2 times sigma power 4 by n. Thus, we can derive the CRBs in the case of a vector of parameters. Thanks for watching.